Hello everyone, my name is Prakhar Chandra. I am the final year student at Thapar Institute of Engineering and Technology, Patiala. My roll number is 101806005. This video is being made for the submission of my final year research capstone project, which is titled as Design of Algorithm for Filtering Out ECG Signals and the Hardware Implementation of its Different Blocks. It is under the supervision of Dr. Anil Singh, Assistant Professor, ECD Department, Thapar University. In this video, I am going to show you the various researches that I have performed during this course of year and their outcomes. So without wasting any much time, let's jump direct over to the video part.
Now, let's understand what is an electrocardiograph or an ECG. The blood flows through the atria, causing them to contract. That corresponds to the atrial depolarization and the generation of P wave. Impulse traveling through atrioventricular node results the flat surface in ECG. Hence, PR segment is flat and no current is flowing through cardiac muscle cells. As the blood flows from AV node to the bundle of His and along the upper part of the septum, the Q wave is produced. The passage of electrical signals through the ventricle produces a large spike called the QRS complex. QRS complex is much larger than P wave because ventricles are larger than atria. QRS complex represent depolarization of left ventricle which has much greater mass than the right. The impulse remains unchanged for a moment. That gives rise to the another flat surface called the ST segment. The impulse fade away and the ventricles repolarize. T wave is generated giving end to an ECG cycle. So here is a list of the different objectives of this project. The first objective is to identify the efficient filtering algorithm to filter out ECG signal. The next objective is to develop the MATLAB code of the identified algorithm. And the final objective of this project is to perform hardware implementation of different blocks of the algorithm. This is the data that is taken under the consideration. This is the data that corresponds to the ECG signal of a patient that is recorded for 4 minutes. The interval of two successive samples is 1 millisecond, so the complete dataset contains about 240,000 samples. This is the frequency response of the data that was shown earlier. If we magnify the frequency response between 0 to 100 Hz, we can clearly visualize that the effective information lies somewhat between 3 Hz to 10 Hz. Once we have decided the effective frequency range, now we can design the filter accordingly. The simplest filter that one can think of is the band pass filter. So, this is the outcome obtained when the raw data was passed through a band pass filter of cutoff frequencies 3 Hz and 10 Hz. Now, as we can see that this filter is not able to detect any component of the ECG signal, so we need a different algorithm to proceed. The algorithm now that we wish to apply is the Pan-Tompkins algorithm. This is the block diagram of the Pan-Tompkins algorithm. The first stage is a low-pass filter with the cutoff frequency of 15 Hz. Then the next stage is a high-pass filter of a cutoff frequency of 5 Hz. Then we have a differentiator followed by squaring, and then we have a moving window integrator, and then in the final stage we have the adaptive threshold. This algorithm helps us to detect the QRS peak. In this project, the first 5 blocks of this algorithm are implemented and the results are analyzed. This is the output generated when the raw data is passed through the first 5 stages of the algorithm discussed earlier. As we can clearly see that the QRS peaks are roughly detected. Now, as this algorithm detects the QRS peaks, so the next step is its hardware implementation. For the hardware implementation, the Verilog code of each block was written and synthesized. This is the schematic diagram used for the low-pass filter. The coefficients were generated with the help of MATLAB. Similar to the low-pass filter, this is the schematic diagram used for the designing of high-pass filter. This is the schematic that was used for the derivative filter. This is the schematic for the moving window integrator. It has 32 buffers and each buffer has the value of 1 divided by 32. This was the hardware generated when we combined the 5 blocks of the Pan-Tompkins algorithm and implemented them on RTX 7 Basis 3 FPGA board. This brings us to the end of the video.
So that's all for my project. I want to thank the Thapar University and ECG department for giving me the opportunity to present myself. Hope you like this effort. Thank you.